Because with Gaussians, if you're arranging Gaussians on a lattice, then the number of Gaussians you need to maintain the same lattice density would go up exponentially with the number of inputs. It's like usually called the curse of dimensionality. So if you're just thinking of having something really simple like 10 Gaussians between your minimum and maximum values, well, if you had one input, you only need 10. If you had two inputs, you need 100. If you had three inputs, you need 1,000 already, and you're trying to compute those in real time. If you have four inputs, you need 10,000. So very quickly, with the number of inputs, these radial basis functions become impractical. So one approach is to try and have some intelligent way of putting the centers of those radial basis functions so that you don't have to use that many. But there's a better way. We have the cerebellar model arithmetic computer. So the basic idea is, rather than using these global Gaussians, is that you select basis function domains that are hypercubes. And this is going to create a lot of computational efficiency for us so that we can handle many inputs. But let's just take an example of two inputs just so we can see how it works. So one layer of the CMAC looks like this. So basically just an array. So my input, in this case, is just vector x1, x2. And basically the index, the input index is one of those array cells. We're going to call them cells. So what we're going to say is the indexed cell is activated. Okay? And CMAC has multiple offset layers. So let's see, it's kind of maybe a bit tricky to draw, but I'll just kind of exaggerate how it works in the drawing. So we'll kind of like make some exaggerated offsets for these cells. Maybe it'll be kind of obvious what I'm trying to convey. So let's make this one way over here. So hopefully it's obvious among those three layers I just drew that those hypercubes all have kind of different domains. They're all kind of shifted, okay? number of quantizations per input is Q, and the total number of hypercube cells is n equals mqn, q to the n. Where m is the number of layers, and n the number of inputs. So let's just kind of try and draw this again. See another view of this. Hopefully I have different colored pens on you because that'll make taking notes a lot easier. So if I had an input x1 and x2, it's going to activate one cell on each one of these layers. So let's say my x2 is here, my x1 was here. And I'm activating this one. I'm activating this one. And I'm activating this one. Oops, not that one. With this point here. Anyway, it's an array. One cell is activated per array, regardless of how bad my drawing is. Make sense? So the output is f hat equals the sum from I equals 1 to m gamma I of x wi, i.e. only the activated weights are included in the output. So you can see where the big advantage is. If I was writing the same expression for a radial basis function network, I'd have the sum equals I to capital N, where N is the total number of basis functions in the network. All of them. This one is only little m, just the number of layers in the CMAC. So this doesn't go up exponentially as the number of inputs. I could just have m equal to 10 or m equal to 100 or something, regardless of how many inputs I had. So my number of online calculations doesn't go up with the number of inputs. So it's always computationally feasible to apply the CMAP. So if I was controlling a system with less than 4 inputs, I would definitely use radial basis functions. If I had like 4 inputs, I might think about whether I'd use radial basis functions or CMAX. But if I had 5 or more, I would definitely use the CMAC. It'd be like really too difficult to try and implement radial basis functions. Okay, and I like to use spline basis functions. And in that case, you get gamma I of x is equal to product from k equals 1 to n h squared minus 2h cubed plus h to the 4th. I'll just call this I here, hi. If x is in cell I, it should be hik, I guess. For the kth input, and 0 otherwise. Does everyone draw this messy diagram already? Where HIK is the normalized position in the cell. On input K. So if I was to draw it, so I said I like to use these splines. The big thing is that they are differentiable, which turns out to be really important for the flexible joint robot. It turns out for the flexible joint robot, we'll have to have differentiable basis functions. So yeah, I like to use them, but also you have to use them if you're doing flexible joint robot. The other options, you could use binary basis functions, you could use triangular basis functions. You could even use Gaussian if you wanted to, but they would be discontinuous at the edges, which is kind of not so nice. So there's all kinds of basis functions you could use here. There's no like one correct answer. But splines have this nice feature that they go to 0 right here and here at the edges of the cell, so you get a continuous output, and that they're differentiable. So those are kind of the two big features that I really want from the basis function. And when you look at the computer code too, I won't do this literally, I'll normalize just like I did for the regular basis functions. So I'll take this, and then I'll divide by the sum of all the other basis functions. So I have a nice normalized spline. Okay. I really didn't want to go over 2 hours, but I'm going to go for 5 more minutes, so hopefully you aren't too mad at me. So I'm almost done this CMAC, so I might as well finish. Anyway, does this make sense so far? And then, so this is what it looks like on each input dimension, and then I just multiply these all together because I have multiple dimensions, multiple inputs. So it's just the multiplication of all these little spline basis functions. So there's one more thing about the CMAC, and then I don't want to just allocate arrays. The one thing is kind of a pain to allocate a 10-dimensional array, even in MATLAB. And for the other reason is that a 10-dimensional array would probably very quickly consume all your computer memory before you even got to 10, actually. So, problem n equals mq to the n is too large to allocate in memory. Solution. Most cells are never activated anyway. So just use random hash coding to store the weights. In a small physical memory. Because basically, if you're going through 10-dimensional space, well, there's a good reason why you'll probably never go through all the cells in that 10-dimensional space. Because if it was a robot, then for the robot to travel through all the cells in that 10-dimensional space would probably take more than your lifetime. You could probably just sit there and watch the robot try and go through all that 10-dimensional space. You'd probably die before it even managed to do that. It's big space. You get that many dimensions. So really you're talking about traveling through trajectories in that 10-dimensional space. So the vast majority of those cells will never be indexed, and all their weights will stay 0. So you don't have to allocate memory for them in your computer. You can just do this random hash coding. And I'm giving you the code for how it works, so I don't really have to write all the code on the board, but I'll just draw a diagram of how it works. You basically have your virtual memory here. And each spot in the virtual memory will map to a one-dimensional array physical memory. So the idea is you get a random mapping and occasionally they will map to this same space. So this is what we call a hash collision. So the idea is to choose your physical memory large enough so that hash collisions are extremely rare and don't really affect your control system. So choose physical memory, memory as large as possible. So hash collisions are extremely rare. and shouldn't really affect anything. So does that kind of make sense? Okay, so I'll show you like a little computer simulation of the CMAQ working. And I'll provide the code for you on D2L so you can play with it yourself. So I'm going to do this a little bit differently than the way I did the radial basis function. So with the CMAQ example, I'm going to set this up so it's like a static training. So I'm going to pre-train it. So in this case, I'm not going to do an adaptive control. I'm going to do like a pure neural network control. So this is the nonlinearity that's in my system. So what I'm doing in this example is I'm actually measuring that nonlinearity, and I'm training the CMAQ to approximate that nonlinearity. And so what I get out of the CMAQ, it looks like this. So you can see that it's not a real accurate approximation of that nonlinearity. But for control system purposes, it's more than accurate enough. You don't actually need that much accuracy to get a good control system out of it. Like if I was using Gaussians, this would look way smoother than the CMAQ. So the CMAQ doesn't produce the really nice smooth approximations you see of the Gaussian network. But it basically is good enough for control system purposes. So if you're interested, this is like what's happening on some of the different layers of the CMAQ. So basically these are the different layers of the CMAQ, and all these outputs get added together to give you that graph that I showed you in the other graph. So I think I'm using a 10-layer CMAQ here, and these are just 4 of them, just for example, so you can see what's happening inside the CMAQ. So all these things get added together to give me my output here. And so I'm going to use this in the control system because that's my nonlinearity that I'm going to try and cancel out with my controller. And I'm not going to update the weights during the simulation, so I'll just leave it static. So I'm trying to cancel the nonlinearity using this approximation. So you can see that the training for the CMAQ was super simple. I just have my error, so I'm assuming I can measure the nonlinearity. So the nonlinearity minus the CMAQ output gives me my error. And I just multiply that by the basis function value, multiplied by a little training factor, beta, that should be between 0 and 1. So it's called gradient descent learning, very simple, just updating based on my output error. And then I can use this in the, let's see, take a look at the, you can take a look at the system I have set up here. So my nonlinearity is cos 3 times x2. And so that's plus 2 times x3. So this is my nonlinearity that I'm trying to cancel out. So I set up a feedback control here. So I just have like a position error and a velocity error in my feedback control added to the output from the CMAC. And I'm seeing how that will work. And again, I'm just using like sinusoidal input trajectory. So let's see how it works here. So one thing I'm graphing is I'm trying to see how much my CMAC is doing versus how much my feedback control is doing. So you can see that initially the feedback control does most of the work. So here I have it on a logarithmic scale, so you can see because it's kind of squeezed in here at the beginning, you can't really see. So I just expanded it on a logarithmic scale. So you can see initially the CMAC doesn't really isn't doing as much as the feedback control, but then after a while you can see that most of the output actually comes from the CMAC rather than the feedback control. And so you can see that it does take a little while to go into the desired trajectory. So remember, there's no actual training going on here of the CMAC. The CMAC is just static in this example versus different. Like if I was training the CMAC adaptively, then I would see some error the first time, but it would be like perfect by the second time. So that's kind of a big advantage. Another advantage of having things adaptive is they will react even faster. And what else did I want to show? Where'd that other graph go? I did have another graph here. Oh, I guess my other graph was for my training. Yeah, I forgot. I guess I didn't show this graph the first time. Here, let's run the training again. Yeah, I forgot to show you this when I did the initial training. So this is basically, so I'm going back and forth across this nonlinearity and then back and forth again. So one complete circuit of this nonlinearity is basically one trial or one epoch in the training. So this is the number of times I have to train the CMAC before it's converged. So you can see that basically by the fourth training iteration, I've gotten pretty close to where I'm going to get to. So it's almost converged within 4 iterations. And then there's a little bit of fine tuning. And then by about 10, I don't really improve much beyond 10 iterations. So CMAC basically learns in about 10 repetitions of trying to learn something, which is extremely fast. So, most people, when they say neural networks, they talk about backpropagation networks. Multi-layer perceptrons is kind of usually what people mean when they say I'm using a neural network for something. But if you're using a multi-layer perceptron, it would take like at least 100 before it would get down to this level. So the CMAC trains like 10 times faster at least than a standard multi-layer perceptron neural network. So that's why we like to use them in control systems, because in control systems, you don't really want your robot to have to do a trajectory like 100 times before it's learned it. Like you really want to have your trajectory, done pretty accurately, hopefully by the second or third time. Like you really want, your robot to learn things really quickly, otherwise it's kind of useless. So that's why we like CMACs in control systems, because they can kind of adapt really quickly and train really quickly compared to these other kind of neural networks. And like I said, the advantage over radial basis functions also train this quickly, but they can't handle the large number of inputs. So in a lot of ways, CMAC is kind of the ideal neural network to use in control system applications. Okay, does anyone have any questions about CMAC?
Are they used commonly in like other applications, like just neural network applications? Like if they train that fast?
Yeah, they're not really commonly used, but you wouldn't necessarily say neural networks are commonly used in control systems anyway. But this is radial basis functions are really commonly used. So they're definitely people. You see people use radial basis functions all over the place. And then when you get into a lot of inputs, then people kind of have a wide variety of things they try to use to deal with multiple inputs when you have like more than 4 or 5 inputs. So there's like people have differing opinions on what the best way to go with is with a large input system. So obviously my opinion is to use CMAC, but other people don't agree with me on that, and other people use different kinds of systems. So like I said, you can use radial basis functions where you try and be more intelligent about where you're placing the centers of the radial basis functions. But which is okay for one trajectory, but if you think that your robot might be learning many different trajectories, then it doesn't really make sense anymore, even with the radial basis functions, whereas the CMAC is certainly capable of learning as many trajectories as you like. So it kind of depends on the application of it. I mean, some robots do only one trajectory for their entire lives, in which case maybe a radial basis function network that's kind of tuned properly would be fine. But if you're talking about a more general purpose robot, CMAC probably makes more sense. And as far as the rigid robots go, like I'm pretty confident that you wouldn't be able to show anything could work. Neural network would work better for a rigid robot. But like I said, with a rigid robot, you can set up an adaptive design with adaptive parameters pretty easily. So there's really not that much reason to use neural networks in rigid robots. You can probably just do an adaptive design, which would outperform the CMAC. But we're going to get to these flexible joint robots, and in the flexible joint robots, an adaptive design is really difficult. This is where the CMACs will really come in handy. And in the flexible joint robots, we have 14 inputs because we have 2 positions and accelerations for each joint, and desired positions, velocities, and accelerations for each joint. So it all adds up to 14 inputs. So the radial basis functions really won't do the job. You can't have a 14-dimensional array of radial basis functions. Any other questions? So in the next class, I will teach backstepping, which means that everything we've learned about rigid robots, you'll suddenly be able to apply to flexible joint robots once we learn the backstepping technique. So I'll teach that to you in the next class. Okay? All right, so we'll see you next Monday.